The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. This is Rick Kosick with GoldSim Technology Group. We're going to get started just in a minute here. We're going to, a couple more people seem to be arriving. Uh, could you do me a favor? Could you just raise your hand if you can hear me? I just want to make sure that people can hear. Okay, great. That sounds good. Um, let's just give it another couple minutes here as a couple more people trickle in, and then we'll get started. Okay, I think we'll start now. Uh, Today, what we're going to be talking about is representing discrete changes in water management models. Um, the features I'm going to be discussing are actually pretty basic features in GoldSim. They're pretty simple features, um, but not a lot of people necessarily are aware of them or use them. So we thought it'd be worthwhile to put together a little webinar here where we discuss these features. So when I say discrete change, what do we mean by that? Well, if you think about models that you build, um, you're simulating how systems change through time. For most water management models, we really are thinking in terms of continuous changes. Water is flowing, so we're thinking that uh, water levels or flow rates are changing continuously throughout time, and that's obviously what happens. And in terms of the mathematics, we're solving differential equations. But other things in a model can actually move or happen discretely. Um, so in the example of a water management model, we turn on and off a pump, and turning on and off a pump is an instantaneous um, feature, and so it doesn't happen continuously. It's a sudden occurrence. Uh, Other examples would be things like an equipment failure or an accident. Just because something is considered to flow like water, it doesn't mean that all of your dynamics can be treated as being continuous. Um, what we're going to talk about today is representing these discrete changes to the system state. A pump is on or a pump is off, for example. And if we really want to represent that, we need to use the features that I'm going to discuss today. In the real world, most systems truly are a combination of continuous and discrete dynamics. We tend to often ignore the discrete dynamics, but they can be quite important. So just to give you some examples, here's a really simple example. Let's say I had a bucket of water. Um, if I were to poke a hole in the bucket, uh, that's an event, and instantaneously water would start leaking out of the bucket. If then I plug the hole, water would stop leaking out of the bucket. But it's important to realize that the definition of what we mean by instantaneous is really relative. It's relative to the time frame of interest. So in this little trivial example, I'm looking at a bucket of water, let's say over 60 minutes. Obviously, if I poke a hole in it, it's not instantaneous. Maybe it takes a couple seconds for me to poke that hole, and then it might take a couple seconds for me to plug that hole. Um, but that time frame is short enough to be considered instantaneous relative to the time frame of interest, in this case 60 minutes. Uh, if we were modeling some money in an account, um, the financial transactions that add money or withdraw money to the account are events that we can consider to be instantaneous, and they probably are pretty close to instantaneous. It's an electronic event, right? And so we have, in this example, two deposits and 2 withdrawals. And in between that, we have, let's say, continuous compounding of let's say, the interest. And so we're having a continuous change that's occurring, but superimposed on that continuous change are just these discrete events. So in order to model these discrete changes of state to a system, we need to represent what I've been referring to as events. And what do I mean by an event? Well, you can generate events in GoldSim in 4 different ways. You can specify a rate. So you can just say this event occurs once a week or once every 10 days. And when you specify a rate, it can be a regular rate or it can be a random rate. So a regular rate would occur exactly every 10 days. A random rate, on average, would occur every 10 days. With respect to water management models, one of the most important types of events would be an event that occurs when a specific condition is met. So the water level is greater than 10 meters. When that becomes true, we're going to do something. Let's say turn on a pump, for example. We can also create an event not when a condition is true, but just when any variable in our model changes. So we can monitor any variable in the model and say, when this changes its value, trigger an event. And finally, we can specify events to occur at specific dates or times. So we can say this event occurs every day at 8 a.m. Or this event occurs on the first Friday of November at midnight. Or we can say this event occurs 50 days into the simulation. So we can put a time, a specific time on when an event would occur. So the reason we're triggering events is when an event occurs, let's say when a water level exceeds a certain value, we care about events because we want them to trigger some other element in your model to take a particular action, to instantaneously change its value, for example. So let's just talk about some of these events, and we'll start to look at some models. So this is the idea of generating an event that is either regular or random. So I'm going to show you a little model here where we're going to create an event that occurs once every 20 days. And the element we use for this is called a timed event. So if we open up a model that shows a timed event, here's our timed event. I've said it's going to occur at regular time intervals once every 20 days. That's what its occurrence rate is. And if I run this model, I can plot, one of the outputs is the number of events, the event count. And if I go ahead and plot that, you'll see, well, it occurred once every 20 days like we asked it to. This is a similar event, but I've said that it occurs at random time intervals. And mathematically, we're going to represent it as a Poisson process, which has some particular statistics I won't get into, but it's a very common way to represent random events. You can represent random events using other types of statistics too, but the most common way is to assume it's a Poisson process. So these two models, that's a regular event, random event. Here I'm plotting both of them on the same curve, and you can see in this particular case, this one realization, they both occurred 5 times, but the random event occurred, it didn't occur regularly. It just happened to occur 5 times, but it doesn't have to. In fact, I'm going to rerun this model, and I'm going to run multiple realizations. Let's run 1,000 realizations of this model. And if I do that, and now I look at the random events, that realization right there, realization 1,000, no events occurred. Not a single one, right? 2, 5, 6, 4, 5. We kind of click through here. If we look, here's one where we had 7. There's 1, right? We can look at a distribution of the number of events that occurred, and you can see it looks like this. And the mean number of events was indeed 5, but that's the distribution of the number of events that would occur if you simulate an event as a Poisson process with an expected value of 5. You can see there was a 0.7% chance there were no events at all, and a 0.2% chance there were 13 events. Right? That's just the statistics of that type of process. So that is a fairly simple type of way to generate events. But for water management models, we're typically going to do something a little bit more interesting. The key point is, if we're going to generate events, we only bother to do it if they're consequential. They do something. And when I mean by doing something, they trigger other elements in the model to do something. It turns out a number of elements in GoldSim can be triggered by an event, and all elements that can be triggered share the same triggering dialog. The triggering dialog looks like this. And we're essentially going to say this is the type of event that's occurring, and we're then going to give it a definition. So this little drop-down list will have a number of options to define the type of event that you want to create. So let's create a simple trigger and then look at how it affects an element in our model. So we're going to stick with this very simple type of event. This is a random event that occurs once every 20 days. But now we're going to have it do something. And what it's going to do is it's going to trigger a stochastic element. A stochastic element is one of the elements that can be triggered. And stochastic elements can be triggered if you want to resample them. So basically, every time you trigger a stochastic element, GoldSim picks a new value. If you don't trigger a stochastic element, it picks a value at the beginning of the simulation. So if I were to insert a stochastic element here, it would say sampled once, and it would pick a new value at the beginning of the realization. But if we want to resample it, we click this little button that says resampled, and that then activates the triggering dialog that I just spoke about. And the triggering dialog looks like this. And in this case, it says, when the event called random event occurs, resample me. Quite simple. So if we run this model, I'm plotting here, the red is the number of events, and there were 5 events, 5 random events that occurred, and every single time the event occurred, we just picked a new value for that stochastic. So pretty simple. But let's now look at other more interesting ways that we can generate, we can respond to an event. This time I want to trigger that stochastic using a condition, right? Remember what I mentioned, that we can generate an event when a specific condition becomes true or false. So let's look at a model that does that. In this model, I'm keeping track of fuel in a tank, let's say, right? So I start out with 100 gallons of fuel in this tank, and it decreases at a rate of 0.5 gallons per day. So that's all we're doing here. We're keeping track of fuel in a tank. Very simple model, just goes down linearly. But what I'm going to do here is I'm going to tell GoldSim that I want to resample this stochastic now whenever the fuel drops below 71.7 gallons. And the way I did that, I said this is an on-true trigger, an on-true trigger. And what an on-true trigger says is, when this condition right here becomes true, pull the trigger. It's not when it is true, when it becomes true. So this trigger is going to get pulled when the fuel is at 71.7 gallons, but when the fuel is at 72 gallons, it won't be pulled again. It's only when it becomes true. It could become true multiple times, of course, because if the fuel were decreasing and then we were to add some fuel to the tank and then it would start decreasing again, it could be this condition could become true multiple times. In this simple model, it's only going to become true once. And so if we look at this model here, all I did, again, we're not doing anything interesting in terms of the response. We're just resampling the stochastic. But you can see once we got down to that level, the stochastic, we picked a new value from that stochastic. Now we need to point out something that's critical to understand about events here. When do events occur? When do events occur? Did this event really occur when the condition, when the fuel became less than 71.7 gallons? Actually, it didn't, right? An on true trigger, what it really says is the next time you look, check to see if the fuel is less than 71.7 gallons. Well, how often are we looking? Well, we're looking in this particular model every day because we have a 1-day time step, right? So if it just so happens that the fuel becomes less than 71.7 gallons exactly on a time step, yeah, then this is true. But that's not the case here. This says on true, see if this is true the next time you check, right? So this particular event, when it really occurred, is if we look down here, when we resampled the stochastic, you can see we resampled the stochastic at 57 days, right? And somewhere between 56 days and 57 days, we went below that 71.7 days, right? Actually, it happened very close to 57 days. So that's how this type of trigger works, but we can change that. I can say instead of being an on true trigger, I want to do an at stock test trigger. And this is going to be really critical for water management models. I'm introducing it in a very simple way here, but you're going to see in a little bit, you're going to see how this plays out in a water management model. And that stock test is way more powerful. It also makes the simulation run a little bit slower, but it's way more powerful. And that stock test actually monitors that condition continuously. And it inserts a time step when that condition is true. And the way we're going to see that is, you recall that GoldSim, we've talked about this in many other webinars, GoldSim can insert time steps when certain things happen. In a water management model, the most important of these is when we hit an upper or lower bound, GoldSim inserts a time step at that point to represent it accurately. Well, we're going to do the same thing when an event occurs. So if I come in here, I'm going to actually monitor this. I'm going to say include unscheduled updates in time history. So I want to actually see this just to demonstrate to you that this is happening in the middle of a scheduled time step. If we now run this model, you're going to notice that what happens here is that's when the event occurred. The event occurred at 56.6 days. At 56.6 days, we hit 71.7. GoldSim inserted a new time step at 56.6 days. Then it continued and it did another time step at 57, 58, 59, and so on. But it inserted a new time step when that trigger was pulled because we told it to. The first time it didn't do that. It just said, I'm going to wait till the next time I look. Here it's continuously monitoring. And the way this works is if you have what's called an at stock test, the condition that we put in here has to be referencing a stock element. And the stock element is an integrator, a reservoir, or a pool. All right, so that's what we're going to be monitoring for this test. Let's talk another thing about triggering. What if you needed to trigger multiple elements simultaneously, right? So something occurs And because of that, you want to influence multiple elements. Um, Obviously, one way you could do that is you would just, you could type in this condition over and over and over again. But GoldSim provides an easier way to do that. Um, it provides an element called a triggered event, right? Or uh, so basically, what we're going to do here is instead of uh, this guy here can monitor multiple events. So the event occurs here. Each stochastic is triggered by that same event. We can and this is quite common in models, right? One event just doesn't affect one guy. We want the same event to affect multiple people, right? And that's what we're going to do here. Now, what we just talked about wasn't very interesting. All we are doing is triggering a stochastic to resample itself. But a variety of GoldSim elements can be triggered by events. Each one responds in a particular way. In the case of a water management model, one of the most common ways you're going to respond to an event is to cause some discrete or sudden change to a quantity, right? You're going to add water, right? Or you're going to subtract water, or you're going to move water instantaneously from one location to another. So let's just look at a simple example. So we're going to start with a pond, and we're going to make something happen instantaneously. Let's say 65 days. In particular, I want to add water to this pond at 65 days, right? So I'm going to open a little model that's already built here. And it's just a model of a pond that's got some inflows and then it's got some evaporation. So if I were to run the model, the pond just kind of fills up with water and then reaches some steady state. So that's what's happening in this model. I want to now add water instantaneously to this pond. And we'll talk about what we mean by that, but let's go ahead and do that. And the way I'm going to do that is I'm going to use something called a discrete change element. A discrete change forces a discrete change onto a quantity, such as a reservoir or a pool. And I'm going to say, let's say change, I'll call it discrete change to pond. And what we're going to do is we're going to give it some quantity. In this case, we're going to say 25 cubic meters. And now we have to give it a trigger. When does this discrete change occur? And now there's my triggering dialog, and I'm just going to now say at E time 65 days. So I'm going to trigger this to happen at 65 days. So what I've got is this discrete change object that says when this trigger occurs, do something. And what I want you to do is I want you to add 25 cubic meters. Well, who do you add it to? Well, if we come over to our pond here, you'll note that there's, in addition to inflow rates, so we have inflows and outflows from this pool element, we also have additions and withdrawals, and these are discrete. We're going to do a discrete addition. We're going to click this box, and we're going to type in discrete change to pond. By the way, this guy right here, I should note, is a special object. This output is called a discrete change. And this guy right here is not, if I were to type in 25 cubic meters, GoldSim says, I don't know what you're talking about. We're going to say discrete change inputs must be defined by a link to a suitable output. The reason I can't just type in 25 cubic meters because GoldSim says, when? When do you want me to add 25 cubic meters? You're not giving me enough information. But this element up here has all the information I need. This guy says, I want you to add 25 cubic meters when this event occurs. And if we go ahead and run the model, we'll see there's the addition We instantaneously added it and then he drained off. Now, again, we say, what do we mean by instantaneous? Well, again, this is a 100-day model. We really can't add water to a pond instantaneously. It takes some amount of time. Maybe it takes minutes, maybe it takes seconds if you drop it from a helicopter or something. But relative to the time frame of the simulation, it's considered to be instantaneous. So now let's change this a little bit more. Now let's say I don't want to add this water to the pond. I want to remove it from the pond. So I just take the exact same output and I put it into a withdrawal from the pond. And now that I withdraw it from the pond, now it pulled out of the pond. Now, if I'm going to withdraw it from the pond, let's say I'm sending it someplace else. So I'm going to send this water to another pond. We'll just create another stock element and we'll call this pond 2. He'll start empty. And now I have to give him a rate of addition. But what am I going to give him? How do I do that? Well, now that I've got a discrete change, this guy's got an output called discrete withdrawals, right? That's a discrete withdrawal. We just made a discrete withdrawal. I'm going to take that discrete withdrawal and put it into that guy right there. So I'm going to say pond discrete withdrawals, and now we're going to push it into this one. You notice these guys are red, right? Red means event, right? Red means this is a discrete change that's happening in our model, as opposed to the black, which is a continuous variable. And now if I plot both ponds in the same curve, you can see that instantaneous withdrawal created an instantaneous addition. Obviously, if you're balancing water in your model, you need to do things like this, right? You want to, if you're going to withdraw something instantaneously, you want to send it someplace typically. Okay, let's look at an example that's similar to what I showed you, but it's going to be a little bit more complex, a little bit more realistic in what you would do in a water management model. So here I'm adding water, which we've just done. Very simple. Here's our pool. I'm adding water, but I'm also withdrawing water. But in this case, the amount of water that I'm withdrawing is random, right? So I'm going to randomly, at a random rate, I'm going to withdraw water, right? And the amount of water we withdraw is also random, right? Whereas this guy up here, the trigger was every month, I want you to add water. So here's this on change trigger I talked about. Once a month, the beginning of the month, whenever the variable month changes, remember GoldSim has a variable called month, which goes from 1 to 12. When that variable changes, add 60 cubic meters of water to this pond. But then I'm going to have a random event that occurs. The random event occurs at a particular rate once every 50 days. Whenever it occurs, I want to remove water. How much water do I want to remove? I'm going to sample how much water I remove from a distribution. So you see that this event is doing two things. It's going to sample the amount of water, and then that amount of water goes in here. And GoldSim, of course, is smart enough to make sure it samples that before it removes the water. But we're going to put one more twist on this element. We're going to say our trigger is going to be a little bit more complicated. We're going to say, when this event is pulled, I want you to check to see if the month is greater than 6. If it is not greater than 6, ignore the event. What we're saying here is we only want this event to occur in July through December, right? So we're gonna generate an event, and then we're going to decide, should we ignore it or should we use it? So we have these advanced trigger options that essentially allow us to modify what we've put up here. It says, look at the event, check to see if this condition is true. If this condition is true, pull the trigger. If it's false, throw out the event. So if we were to run this model, what we'd see is we had no withdrawals. We just had a constant addition for the first 6 months. And then the last 6 months, we had a series of random withdrawals, but they only occurred July through December. So the point here is you can do some pretty complicated things with these triggers. There's lots of features, and I didn't discuss one of the features. That's this ability to wait for a precedence condition. So what do I mean by wait for a precedence condition? So when I have an event occur here, I have a couple options to modify the event. I just showed you we could say, when the event occurs, check to see if this is true. If it's true, pull the trigger. If it's false, ignore the trigger. If I would have put that here instead, month greater than 6, what it's doing now is says, when the event occurs, check this condition. If this condition is true, pull the trigger. If this condition is false, hold on to the event. And as soon as this condition becomes true, pull the trigger. So whereas in the second case, it threw out the trigger if the condition was false, in this case, it waits until the condition becomes true and then it pulls the trigger. So you can imagine in a water management model, you might say, oh, I want to turn on a pump, but we're going to wait until some other conditions are met, and then I'm going to turn on the pump. So we've triggered some condition to turn on the pump, but now we're going to wait until something else becomes true, and then we're going to turn on the pump. So you have a lot of flexibility and power for defining these events. So the next thing I want to talk about is probably the most important for these types of models. In many models, the things you're changing, I just talked about adding water or subtracting water, and that happens sometimes. But the most common thing we want to do in a water management models, we want to discretely change the state of the system in a binary manner. And what I mean by that is there's an on-off switch. The pump is on or the pump is off. The pump is operating or it's not operating. The facility is open or the facility is closed, right? So it's either a yes, no. And those yes, no's happen suddenly. The facility opens up at 8 a.m. and closes at 5 p.m. The pump turns on when the water level becomes greater than some certain number and turns off when the water level drops below a certain number. So many of the changes we want to implement are truly binary in nature. So how do we do that in GoldSim? GoldSim is going to provide two elements that really allow you to easily monitor and act upon system changes that are binary. And these are really powerful elements, and we rarely see them used when people send us models. Obviously, there's some users who take advantage of this, but there's many users who are not aware of it. It's pretty simple, but it's really worth while kind of going through this example. So I'm going to start with an example of a status element. A status element looks like this guy right here. And I'm going to walk through this really simple model. What we're modeling here is not a water management system, it's a conveyor belt, because it's easy to imagine. And what's going on with this conveyor belt is we're modeling the conveyor belt using a material delay. And a material delay just takes an inflow, in this case, the rate at which we're loading, and then there's a time. How long does it take to get through the delay, right? And in the case of a conveyor belt, that conveyor delay is just a function of how fast the conveyor belt is moving and how long it is, right? And so we're going to add stuff to a conveyor belt, and then it's going to go into a stockpile. But we're going to say that this facility only operates from 8 a.m. to 5 p.m. So outside of that time, the conveyor belt stops. It's no longer loaded. All right. So how are we going to model this idea that we're not going to load and move the conveyor belt um, outside of these hours? Well, what we're going to do is you're going to use a status element for that. And the status element is going to keep track of, is the facility operating or is it not operating? So for the delay time, we're going to say, if the facility is operating, the rate at which the conveyor belt is moving is conveyor length divided by conveyor rate. Otherwise, it's some big number. Obviously, a huge delay time is equivalent to saying it's not moving. But we're also going to stop the loading rate. So if the facility is operating, we're going to have some specified loading rate. Otherwise, we're not going to put anything on the conveyor belt. So that's what we're doing. We want to reference whether or not this is operating. In order to do that, we're going to use a status element. And the status element is quite simple. Status element is just an element with two triggers and an initial condition. So his initial condition is false. All right, I'm not operating. What's the trigger to make me true? In this case is when the hour becomes 8. When hour equals 8, the facility stops operating. What is the trigger to set me the false when the hour equals 17? And so this is now going to model, if we were to just run this and look at operating, it's just keeping track. It's a 0 or a 1, whether or not the facility is operating. But now, since we're referencing it in the conveyor delay and the loading rate, we can actually model what's happening here. And what's happening is there you can see it loading, right? So we're loading the stockpile in a stepwise fashion during after 5 p.m. and before 8 a.m. we're not loading the stockpile anymore. Very, very simple little model, but it allows you to reference something that's turning on and off. Let's go make this a little bit more complicated, and let's look at a milestone element. So in a milestone, we're going to keep track of when a particular thing happens, and then we're going to be able to reference that. So in this case, I want to say when the stockpile hits a certain size, shut down the entire process. Stop loading the stockpile. And my milestone element looks like this. The milestone element just has a trigger and says, when do I occur? When is this milestone reached? In this case, the milestone is reached, I'm using an @stock test here, when the stockpile is greater than 20,000 kilograms. All right, that's when it's reached. When it's reached, I now want to reference operating. And I'm going to come over here, I'm going to set it to false. I'm going to say, I want to shut down the facility at hour 17, but I also want to shut down the facility when the stockpile, when the milestone is reached. And the milestone has an output called completion status, which is true in this case. And it says, so when this milestone is reached, shut down the whole facility. So if I run this model now and look at the stockpile, now we see a different result. In the middle of this day, we reached that peak and we stopped and we never reopened, right? And why did we never reopen at 8 o'clock? Well, the 8 o'clock trigger says, turn me back on at 8 o'clock, but only if I haven't already accomplished that milestone. Right, so the combination of these two elements really give us a control over this binary this binary condition that we want to monitor. Now, what I'm going to talk about next is probably the most important issue for water management models, and it's using status elements to monitor a feedback control system. And most water management models have a whole bunch of feedback control systems in them. What is a classic feedback control system? Well, you're turning a pump on and off, right? In response to a water level. If you don't use status elements to do this, you can run into big problems. In particular, you can get oscillations in your models. And of the models that are sent to us for debugging, this is probably the most common problem we see when people send us a water management model. They say, my model is oscillating, I don't understand why. So let's talk about an example of that. Let's say we have an empty pond and we're putting water into it at some flow rate, around 100 cubic meters per day. We want to try to keep the volume at 300 cubic meters per day by turning a pump on and off, right? The pump pumps at a higher rate than the inflow, so we can easily kind of control the water level. So when people look at this, say, well, how would I do that? And their first uh, idea is often to do something like this. If the pump is greater than or equal to the target, so if the pond exceeds 300 cubic meters, turn on the pumping, else turn off the pumping. And although this looks logical, this results in oscillations. So let me just show you an example of that. That's the model I just described. We've got some random inflow coming in. We have a target, and we basically say, I'm going to turn on pumping at a particular rate. When we get to the target, if we're below the target, I'm going to turn it off. If I run that model, I'm just going to get oscillations. Basically, it'll stay at 300, but it's going to do this. In fact, the number of oscillations is a function of your time step length. So if I made my time step length, let's say 1 minute, it gets really ugly, and we just have boom, boom, boom. This is the pump turning on and off constantly, right? Because as soon as we hit the target, we turn the pump off, and then we have to turn it back on, then we have to turn it back off. Well, that's not obviously how a real system operates. How does a real system operate? A real system operates the same way a thermostat operates, right? So if you think about how a thermostat in your house operates, it monitors the temperature. The heat doesn't turn on when the temperature, let's say, uh, uh, I should say that the cooling or heating. So you might say, well, do we turn on the heat when we drop below 68 degrees Fahrenheit, and then turn it back on when we uh, uh, right at that 6A level? No, that's not really what we do. What we actually do is something like this. So in reality, we turn the heat on, let's say at 68, and then when it hits 70, the heat goes off. When it hits 68, we turn it back on. That's not what your thermostat says. Your thermostat, probably says 70 or something, but that's not how it works, right? It couldn't work that way, because otherwise you would be essentially turning your heat on and off every second, right? Boom, 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 boom. There's always what we call a dead band. This area between 68 and 70 degrees is a dead band. In order for a thermostat to work, we have to monitor two things. We have to know two things. What is the current temperature, and is the system currently on? That's the two things it has to monitor. In a pond example, essentially, we're going to say we want to turn the pump on when the volume reaches 310 and turn it off when it reaches 290. So our dead band is 20 cubic meters. In this case, we're tracking two state variables. What's the volume in the pond, and what is the state of the pump? And we're going to use a status element to track the state of the pump. So let's look at that same model. Now we're going to simulate it using a dead band. And so what I've done here is I've got my pumping rate says if the pump is on, we're pumping at that rate, else it's 0. Well, when is the pump on? We're going to use a status element to simulate whether or not we want the pump on. When do we turn the pump on? We're going to turn the pump on when the pond exceeds some target plus half the band. In this case, the band was 20 cubic meters. The target was 300. So we're going to turn the pump on when we reach 310, and we're going to turn the pump off when we reach 290. And so in this case, when we run our model, this is how our real system would operate. It's still going to oscillate, but it's oscillating in a controlled way, and our volume is staying right there. Obviously, the smaller our dead band, the more on and offs we have, and the closer we remain to the value we want to be at. But that's how a real feedback control system would operate in the real world, and that's what you should try to represent in your models. All right, next thing I want to talk about is interrupting a simulation. This is a feature that's built in the GoldSim. It's not really a modeling feature. You're going to see it's really more of a debugging feature, but it can be very, very powerful. And there's an element that responds to discrete changes in your model, to responds to events, that allows you to interrupt a simulation. So let's look at an example of this. It's a very, very simple example. In this case, I have this pond that's filling up, but I've put in an interrupt element here, and the interrupt element says I want to interrupt the simulation when the pond becomes greater than 102 cubic meters. And so if I run this model, I just pause the simulation. It says volume, it's giving me the message that I wrote there. Now I can pause the simulation and I can look at it. What's going on here? I can plot the result so far, and then I can go on and say, all right, continue on. So why would we want to do something like this? Why would we want to interrupt a simulation? There's a number of reasons why we'd want to do it, but the most common are these two. I want to debug a model. Something is going on. I'm getting a fatal error, or showing some unusual behavior at a certain point in my model. I will put in an interrupt element just before that. Let's say I get a fatal error at 103 days. I'm going to put an interrupt at 102 days so I can freeze the model at that point in time and look at what the heck is going on. Try to debug. Another really common way that I use interrupt elements is to alert me to a logical problem in my model. So imagine you're building a fairly complex model. You can't really run it and test it because it's all in pieces, all right? But you know when you built one part of the model that, well, if this quantity goes below 0, right, or if it goes above 100, I know that there's a logical error in my model because the way I'm trying to program this is it should never go below 0, it should never go above 100. But I'm not going to be able to test my model for a while. I might not be able to run the model for a week because I haven't completed it. So I'm going to put in an interrupt element right there and say, hey, remind me if this ever goes below 0, right? So now a week from now, I finally run the model, up comes my interrupt and says, oh, you dropped below 0, and now you're saying, oh, I must have a logic error somewhere. I'll have to go in and look at that. So it's a very, very powerful way to debug and test your models by just using this simple interrupt element that's just responding to triggers that are usually discrete changes that are usually referencing values, like is the water level above this? Is a particular value below 0? Very, very common thing to do. The last thing I want to talk about is a very powerful feature for water management models, although it's not often used. And that is modeling failures and repairs of equipment. So GoldSim has a module called the reliability module that everybody has. You may not know it, but you have it on your copy of GoldSim. It allows you to model the failure and repair of equipment. So what kind of equipment do we care about? Well, in the case of a water management model, what we care about are usually things like pumps. And if you think about it, you're moving water around a system. If a pump fails, there could be bad things that occur. It could be catastrophic. What if you have a big storm event and one of your pump fails, right? Your pumps fail and now we can't respond to this catastrophic storm event. Well, it may be a low probability of that happening, but we don't know until we model it, right? What's the probability of the pump failing during catastrophic, a big rain event, for example? So GoldSim allows you to model random failures of equipment, right? It relies heavily on the features we just discussed, since failures are sudden events. The pump failed suddenly. So let's look at a simple example of a pond that's modeling failures. So in this particular model, I just have a pond. It's got water coming in at a particular rate, um, somewhat random, and then I'm withdrawing water from the pond. I'm pumping water out of the pond, but I'm going to now model whether or not that pump can fail. And this is a reliability element. It's a fairly complicated element. I'm not going to go into detail about it, but I'll just tell you in general what it's doing. What you do in a reliability element, you explain to GoldSim how can things fail, and you can, these are statistically. In this case, I said, well, according to the manufacturer, they've told me that there's two common failure modes for this pump. The impeller can fail and the bearings can fail. And there's some statistics on that. You know, this happens about every 300 days. This is a particular distribution called a Weibull, which if you study failure, it's a very common distribution that's used to model failures. And so it fails about every 300 days. And here, just to make this model interesting, I said it takes 50 days to repair it, right? It's usually not going to take 50 days to repair it, but you know, maybe it takes a couple hours or maybe a day to kind of replace this pump. So what GoldSim does is says, I'm going to randomly simulate failures. And then when the failure occurs, I'm going to randomly simulate how long it takes to repair it. So this is going to fail about every 300 days according to a Weibull distribution, and it's going to have it's going to take it about 50 days plus or minus 5 days to repair it. Similarly, this bearings failure, this failure occurs about every 500 days, and that takes about 50 days to repair it too, right? When the pump fails, this guy has an output that just says I'm failed, right? And now I'm going to reference that. I'm going to say, if the pump has failed, my pumping rate is 0. Otherwise, it's my 30 cubic meters per day. So if I simulate this, if I run this model, here you're seeing, I ran it 10 times, random failures of the system. In this particular case, because I chose very high failure rates and long repair times, you can see it failed 4 times, and while it was failing, my pond was filling up. Okay, now the pump is working again, up, failed again, now the pump is working up, failed again, right? Here we failed twice, right? Twice, twice, twice. There's 3 failures of the pump, and so on, right? There's 1 failure, right? So what this is giving the ability to do is model these failure rates if they could be important. As I said, all versions of GoldSim have the reliability module. You may not have noticed it because it's turned off by default. It's called the Learning Edition, and that's because it's a little bit limited in that it only allows you to model 10 things, let's say 10 pumps. That's going to be plenty for many systems, right? If you need to do much more extensive reliability modeling, there's a model you can purchase, the module you can purchase. But in many cases, the Learning Edition is all you'd really need. It's certainly enough for you to play with it to say, is this something that's useful to me? All right, so we've covered a lot today, but they're kind of simple topics, and I just want to kind of summarize the things that I talked about. These discrete modeling capabilities. I went through them quickly, and I only covered 20% of the features. These are really discussed in great detail in our online course. So if you go to the GoldSim online course, Unit 13, the entire unit, all it does is describe how we model these discrete events. It goes into it in great detail. If you really want to learn more, just go to Unit 13 and walk through this unit of the course. Maybe it'll take you a couple hours. And it discusses in great detail all the things that I started to discuss here, right? There's also a lot of examples in our model library that deal with events. You can find those. If you want to learn about the reliability module is only 2 elements. There's 2 types of elements in the reliability module. The elements are fairly complex. You can see that it was a complex looking element. But learning the reliability module is not difficult. The the user's manual for the reliability module is only, I don't know, 110 pages or something like that. It's not the 1,000-page GoldSim manual. And it's written such that it's written to be read from start to finish. So it's got a lot of examples in it. You can walk through that, and in a day or two, you would become pretty comfortable with the reliability module. So if you want to dive in more, go and look at um, the manual. And as always, feel free to always send us questions via the help desk. If you have a question on any of the things we discussed today, we love to get your questions. Send us your questions, and we'd love to help you out. Finally, I'll just note, if you have any colleagues who you thought this might have been of interest, we'll be posting this recording and all of the files that I shared with you to our website. We'll probably have them up there probably by Monday. All right. Again, I thank you for your time and attention, and have a good day.